Howdy. Welcome to the first recorded lecture for Multivariable Calculus in the fourth quarter. We are going to start this with looking at double integrals in polar form, which is a natural extension of the iterated integrals that we've done so far, this time just with polar coordinates. So the reason for this is that not all regions that we might want to look at are particularly easy to use Cartesian coordinates for, or even well defined in the first place. So we might look at the double integral of f of xy dA and say, well, what if it's like a disk? So what if it's x squared plus y squared equals 1? If we try and do this with Cartesian coordinates, our best bet might be to put x between -1 and 1 and put y between -√1 minus x squared and √1 minus x squared. But unless we have a very kind function, this is likely to generate a deeply unpleasant integral. This is likely to not be particularly helpful. On the other hand, in polar coordinates, this same disk simply has a radius that's between 0 and 1, and a theta that's between 0 and 2 pi. So there's not actually all that much here that we need to worry about. These are all constants, which generally is going to make the integral significantly easier. Now we can do things in the normal way. We can do an iterated integral in polar form where our boundaries are constant rather than functional boundaries, and more importantly, rather than difficult to handle functional values or functional boundaries. So here, this is something where, since they're constant in particular, we could even justify doing them in any particular order we want, using Fubini's theorem, whatever you want to go with. So quite pleasant as a contrast to what would happen here. The issue with trying to do polar form is that dA, the dA defined up here, is very much in terms of dx dy. dA is kind of a stand-in for dx dy, or dy dx, as the case may be. So we can't just write dA equals dr d theta and then move on with life. That doesn't hold. Instead, we need to figure out some way to turn dA into dr d theta. And so what we're going to do is investigate this with a two-dimensional Riemann sum, this time set up in polar form. So let's take a look at this particular picture where we're starting from the ray defined by theta equal to alpha and ending at the ray defined by theta equal to beta. And then in between these two things, our actual region that we want to integrate across is defined as going from r equals some function h1 of theta and ends at r equals some function h2 of theta. And here I want to show kind of what's happening in these, crosshatch shaded regions. So I've just drawn kind of a crosshatch to represent the way that we would break down this Riemann sum. And specifically, we want to look at this particular little region. So here, kind of drawn alone, is that same region. And there's a few things going on here. First off, it's going from some radius 1 to some radius 2, r1 to r2. And these two radii are very, very, very close together. So we're going to define r2 minus r1 to be dr in the normal way, in the standard kind of Riemann sum sort of way. Very, very similarly, the arc that is defining this particular region is d theta. It's very, 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 very tiny. So tiny, in fact, that this isn't so much an arc right here. This kind of length here is not so much an arc as it is a straight line. Because this is such a small region, we don't have to think of it as circular in really any way. We can treat it like it's a rectangle. So rather than think of this particular region here as an arc, or rather than think of this particular region as some sort of slice of a circle, we can just think of it like a triangle. And what that means is that when we look at d theta here, representing some width, at radius 1, this width is exactly d theta, but at radius r1, by similar triangles, this width is r1 times d theta. So here, the length of this quote-unquote rectangle is just r1 d theta. The width we've already defined was dr. So what that means is the area of this rectangle, and it's small enough, again, this is small enough that we can call it a rectangle, even though it isn't, right? It's certainly not a rectangle. It's defined with an arc, not straight lines, but it's so small that it might as well be. This can be defined as my change in area is equal to r d theta, or r delta theta times delta r, or more to the point, dA equals r d theta dr. And here this r is allowable because R1 and R2 are so close together that they're virtually the same value. So we could think of like dead center in the middle of this shaded region is just kind of R star, in the normal kind of Riemann sum way, where we're just picking a central point to represent the region. Um, and that doesn't change here. Like R1 and R2 can both be treated like there are. So here there's no issue talking about the length being r d theta. Now, obviously, this isn't a rigorous proof that this is an allowable Riemann sum, but it is a reasonable justification thereof. The proof simply needs to create a functional mechanic that says that this is legal, and it's doable. It's simple enough to create that full proof, but didn't seem necessary here. That just getting the idea across seems stronger. So it is the proof simply requires that we justify that the area is the same whether in polar or rectangular coordinates. This is easy enough to justify through functional substitution. But should we justify that, what we end up getting here is, rather than something like f of xy dA, we get f of r cosine theta, r sine theta, r dr d theta. Because again, dA is approximately r d theta dr, or r dr d theta, as the case may be. And obviously, we're just changing to polar form, so x becomes r cosine theta, y becomes r sine theta. More specifically, if we want a more rigorous idea of what's going on here, if f is continuous on a polar region, D, given by 0 less than or equal to h some function h1 of theta less than or equal to r less than or equal to some function h2 of theta, and theta is between some angles alpha and beta, then we get this integral that our original integral fxy, or our double integral, f of xy dA is just going to be the integral from alpha to beta with respect to theta. The integral of from h1 of theta to h2 of theta with respect to dr, or with respect to r, and then the integrand itself is f of r cosine theta, r sine theta, and r dr d theta. Again, recalling x here is r cosine theta, y is r sine theta, and we'll often need r squared equals x squared plus y squared. This 0 less than or equal to h1 of theta, this is only really necessary if h1 of theta is a constant. Yeah, so that's me spending way too long trying to write that with a mouse. But this 0 here um, is only necessary for constant bounds. If your boundaries are functional, then it doesn't have to be there. You can get away without that 0, but it does make things more convenient. So um, if things can be positive, they should be positive. Um, um, but it's more of a weak requirement than a strong one. Everything else in here is a strong requirement. Um, so um, let's actually get rid of that. It's annoying. Um, so moving on to what we actually want to start to look at as examples here, let's go to example 1. So here, this is an excellent example of something where we need to use polar form to integrate this easily. That's not to say it can't be integrated in Cartesian coordinates. It certainly can. You just need to break it apart into 3 separate integrals, each of which would not be exactly pleasant to work with. Well, one of them would, they'd be fine, but you'd have to break it apart, and it doesn't sound fun. Much better just to do it in polar form. So here we can consider this region, below the surface, 3x plus 4y squared, and look for the volume that is generated by essentially projecting onto this region. So what we have here is, again, we start with our normal integral. Our range here, or our region. I was thinking of R for region when I wrote that, but whether we use D or R, for the record, by the way, you'll see both of those. You'll see both R and D. D for domain, R for region. I prefer D. But anyway, 3x plus 4y squared dA. Great and all, but we can change the polar form. So that x becomes r cosine theta, that y becomes r squared, that y squared becomes r squared sine squared theta. dA becomes r dr d theta. And now theta goes from 0 to pi. R goes from 1 to 2. So super easy boundaries. So now we just integrate with, we distribute this r across, integrate with respect to r first, and when we plug things in, we just get the integral from 0 to pi of 7 cosine theta plus 15 sine squared theta d theta. Here, this standalone isn't an entirely pleasant integral, but we have these wonderful things called the double angle identities. And here, that's going to allow us to turn this into a very workable integral. So sine squared theta goes to 1/2 times 1 minus cosine of 2 theta. So if we make that substitution, if we make that change, we just get an eventual integral of 7 sine of theta plus 15 theta over 2 minus 15/4 sine of 2 theta. Now, all the thetas will vanish because we're going from 0. All the sine theta, sorry, will vanish because we're going from 0 to pi. So that just leaves us with 15 pi over 2, and we're done. Do note, this is an example of somewhere where we needed a trig substitution, or we needed to use a trig identity rather. We might need, full trig substitutions in integration terms. We might need to use other trig identities. It might happen that way, but beyond that, things should generally work out nicely when you change to polar form, because the whole idea is you're probably changing to it for a reason. So for the most part, if you're comfortable with your trig identities, if you're comfortable with trig substitution, you should be in decent shape. So let's try another example here. So in example 2, we're going to consider we're going to consider kind of the clover defined by r equals cosine of 3 theta. This is just an area that we're looking for. We want to find the area of the shaded loop here. So what we want to do here is the double integral of just dA. We can think of this in two ways. One is that this is just defining a standard issue Riemann sum of that region. There's no volumes going on, nothing like that. It's just the absolute kind of minimalist. We're just finding a two-dimensional area starting from scratch. Alternatively, it's also reasonable to think about this as a volume of the area, or of the volume that's below the plane just z equals 1. So essentially the idea here is that this is the volume equivalent of the area of the curve simply by having a height of 1. Also reasonable to think of it that way. Both are obviously the idea of just thinking of it as an area we're building from scratch is more correct because that's what we're doing. But the volume facsimile is not a bad way to think about it if it helps. So we need both r and theta here, but these are not that hard to find. Theta goes from negative pi over 6 to pi over 6. That's just where this is going to be defined. That's where this is going to be greater than that's where this is going to be greater than 0. So there and there, easy enough. R goes from theta or 0 to cosine of 3 theta. Well, yeah, it kind of has to. It's r is anywhere starting from 0 out to wherever it hits the end of this loop. So we end up with the double integral. Negative pi over 6 to pi over 6 with respect to theta, 0 to cosine of 3 theta with respect to r, and the integrand itself is just r dr d theta. So here, integrate with respect to r first. Theta pi over 6, we end up with the integral of negative pi over 6 to pi over 6 of r squared over 2 time evaluated from 0 to cosine of 3 theta d theta. Plugging this in, we get 1/2 cosine squared of 3 theta. But before we integrate, we're going to use one of the double angle identities again to turn this into 1/4 times 1 plus cosine of 6 theta. And now we can integrate that from negative pi over 6 to pi over 6, and we end up getting 1/4 times all of theta plus sine of 6 theta over 6, evaluated from negative pi over 6 to pi over 6, and it should be easy enough to justify that yields pi over 12. Mainly because sine of 6 theta over 6 is just 0 for both boundaries. So the last thing we're going to look at is, or the last thing in here at least, is the volume of the region below the plane z equals 10 and bounded below by the paraboloid z equals 8x squared plus 8y squared minus 6. So first off, we're going to try and figure out the boundary where these things meet. So if z equals 10, we're going to get 10 equals 8x squared plus 8y squared minus 6, which just tells us that these two things meet on the circle. 2 equals x squared plus y squared. So that tells us the boundary of where these things of the region that we're going to look at. So theta here, because this is a circle, is going from 0 to 2 pi. R, well, the radius here is always just going to be r squared equals x squared plus y squared, so r goes from 0 to root 2. Wonderfully here, then, the two surfaces are defined on the same integral, and their volumes, the volumes below these two surfaces at least, are defined on the same integral. So we can just combine the integrals. Instead of just finding the two volumes separately, we just say, well, great, we're looking at the double integral of 10, the upper region minus the lower region, so 10 minus 8x squared plus 8y squared minus 6 dA, which we can change to 16 minus 8x squared minus 8y squared dA. But then this just becomes polar form. So we go So we do the double integral from 0 to 2 pi, 0 to root 2 of everything with x replaced by r cosine theta, y replaced by r sine theta, and r dr d theta, which creates this, which once we use the identity that cosine theta plus sine theta equals 1, we end up getting the integral from 0 to 2 pi, integral from with respect to theta, integral from 0 to root 2 with respect to r of 16 minus 8r squared r dr d theta. So here, integrate with respect to r first, get 8r squared minus 2 r to the fourth. When we plug things in, that's just going to give us 8. So we just get the integral with respect to theta now of 0 to 2 pi of 8 d theta, which is 16 pi. And that's pretty much all we need to do. That's pretty much it. So from here, our final step is just going to be to go ahead and just take a look at one more example. But first, just to kind of show the region that we just worked with, I don't want to forget to do that. We'll switch over to, where are you? Here we are. We'll switch over to this. So here, this is the region that we were looking at. You can see this is where these things meet. This is our x squared plus y squared equals 2. If I punch that in, you can see this is generating just the cylinder where those meet. So what we're looking for is, bounded by this cylinder, we're just looking for the difference between the two regions below here, which is what we ended up finding. So what we're going to look at is we're going to look at one more particular region. Specifically, what I want to look at is I would like to look at the area below z equals xy cubed, bounded by the cylinder x minus 1 squared plus y squared equals 1. And what that looks like is just this little region here. That's pretty much it. That's what we're working with here. So let's take a look at how it is that we would go about solving that. So what we're going to do is we're going to go ahead and start by saying that we're just kind of looking at the double integral, forgive my handwriting here, of xy cubed dA. But here, again, this is not going to be a particularly pleasant integral to try and handle in Cartesian coordinates. So we're going to change it. So here, the first thing we would want to know is what are we looking at? And I'm going to require us to simply look at this in the first quadrant only. So if we go back to this graph, the area is taking place entirely in the first quadrant. So we're only going to look at it in terms of the first quadrant. This is what we're actually, looking at here. Here's in the background is the area we're looking for. So if we look at this only in terms of the first quadrant, then what we end up having here is we say, all right, great. It goes from 0 to pi over 2. So that's what theta is doing, going from 0 to pi over 2. However, quite nicely, x minus 1 squared plus y squared also is a relatively easy function to work with. This is actually just r equals 2 sine of theta. Feel free to compute that for yourself if you don't believe me, but when you plug things into polar form and cancel down what you can, you just get r equals 2 sine theta, which is super nice. So moving back to, oops, switch that by mistake. Moving back to our whiteboard, we end up with 0 is less than or equal to theta, which is less than or equal to pi over 2. And we end up with 0 less than or equal to r less than or equal to 2, 2 sine of theta. So here, what that means that we get as a double integral is going to be the integral from 0 to pi over 2, integral, that's definitely an integral, from 0 to 2 sine of theta. And now this is where it gets a bit obnoxious, or this is not obnoxious necessarily, but this is where it gets a bit not particularly pleasant, perhaps, because that x becomes r cosine of theta, and that y cubed rather becomes r cubed sine cubed of theta. And all of this is times r, try that again, times r dr d theta. So, wow, that is obnoxiously bad handwriting over here. Not better. All right. So, putting all these together, we end up with r to the 5th. So when we actually integrate, what we're going to get here is we're going to get an integral of r to the 6th over 6 cosine of theta sine cubed of theta evaluated from 0 to 2. Nope, that's not a 2. Evaluated from 0 to 2 sine of theta d theta. So plugging in 2 sine of theta For r, we get 64 sine to the 6th of theta. Don't worry about this. Okay, it's gone. Good. So what we end up with here is, if we integrate this, we end up getting 0 pi over 2. And now we have, in the end, 64 over 6, which you can rewrite as 32 over 3 if you want. We get 32, over 3 cosine of theta times sine to the, 9th, not 10th yet, times sine to the 9th of theta d theta. And here, there's a pretty easy u substitution to be made of u equals sine of theta. So we're ultimately going to end up reaching, we're ultimately going to end up reaching 32. Again, don't worry about this. 32 over 30 sine of theta to the 10th, evaluated from 0 to pi over 2. But if we just look at what happens when I plug in 0 and pi over 2, something really easy happens. Oh my goodness. Something really easy happens, and that is that pi over 2, sine of pi over 2 is just 1, sine of 0 is 0, so we just have 32 over 30, job done, or more specifically, 16 over 15 as our final area. And that's pretty much it. So that is how we would handle these integrals in extremely messy handwriting tried to be done on a online whiteboard with a mouse. But yeah, that's really what you need to know. So yeah, until next time.